Hi, good day everyone. My name is Jason and I'm the group leader of the group 2. Today, we will be presenting our group project titled Modeling the Height of a Ferry Whale's Passenger as a Function of Time. This project will focus on how we can apply mathematical concepts, especially the trigonometric function, to model a real-life situation. Before we begin, let me first introduce the flow of our presentation. First of all, this is our team. At first, mathematics is not only a theoretical subject, but it can also be used to model a real-life situation. One example is the motion of the ferry wheels, which demonstrate periodic motion, meaning it repeats a regular cycle. As the ferry wheels rotate, the height of the passenger changes continuously over time in a smooth pattern. This type of motion can be represented using a trigonometric function, which are suitable for modeling repeating patterns. In particular, we will be using the cosine function in this project. Next, we will look at the objective of our project. The main objective of this project is to model the height of a passenger on the ferry wheels as a function of time. In order to achieve this, we apply the cosine function to represent the periodic motion of the ferry wheels. At the same time, we aim to analyze the key characteristics of the model, which include the amplitude, period, and the vertical shift. These elements help us understand how the mathematical models relate to the real situation. Now, let's see why the cosine function is chosen. The cosine function is chosen in our project because the motion of the ferry rail started at the highest point when time t equals to 0. A cosine graph naturally begins at its maximum value, which matches this situation. In addition, the cosine function is effective in representing circular and periodic motion, which is exactly how a ferry wheel moves. Therefore, a cosine function is suitable for modeling the height of a passenger on a ferry wheel. With that, I will now pass the presentation to my group member for the next section.
Assalamualaikum warahmatullahi wabarakatuh to Madam Khairun and everyone. My name is Siti Nur Shafira binti Man Azmi. Today, I will present the mathematical model. The motion of a Ferris wheel is periodic, meaning it repeats in a regular and predictable pattern over time. Therefore, it can be effectively modeled using a trigonometric function. Since the passenger starts at the highest point of the wheel, the cosine function is the most appropriate choice for this situation. The general form of the cosine model is shown here, where each parameter has a specific physical meaning. The amplitude represents the radius of the wheel. The frequency factor determines the speed of rotation. The phase shift represents any horizontal displacement, and the vertical shift indicates the center height of the Ferris wheel. Based on the given values, the radius of the Ferris wheel is 20 meters, which determines the amplitude of the function. The center is 22 meters, representing the vertical shift of the model. In addition, the Ferris wheel completes one full rotation in 60 seconds, which defines the period and is used to calculate the frequency factor. Since the motion begins at the highest point, there is no horizontal displacement, and therefore the phase shift is 0. These values will now be used to construct the mathematical model. Now, I will continue how the substitution process happened. First, the amplitude and vertical shift are substituted into the general equation, giving the initial form of the model. Next, the frequency factor is calculated using the formula 2 pi divided by the period. Substituting the period of 60 seconds gives a value of pi over 30. Finally, all the values are substituted into the model to obtain the complete equation that represents to the height of the passenger as a function of time. Next, I will explain the final equation and real-life interpretation. The final model we got after the substitution process is 20 cosine pi over 30 t plus 22. This is the final equation that models the height of the passenger over time. From this model, the maximum height reached by the passenger is 42 meters, while the minimum height is 2 meters above the ground. The model also shows that the Ferris wheel completes one full rotation in 60 seconds, which reflects the actual motion of the system. Therefore, this mathematical model accurately represents the real-life behavior of the Ferris wheel and provides a clear understanding of how the height changes over time. Now, I will pass to the next presenter.
Thank you, Fira. My name is Nurul Fatihah binti Ghazali, and I will start explaining about the graph of the ferry wheels. So, from the equation given by Fira, we need to extract a little bit information first. So, we need to find our A, which is amplitude. As we can see from the equation, our amplitude is 20 here. Okay, so from here we could see that it is in a positive number. Since it is positive, the graph will looks like this. From the top goes to the bottom and then it goes to the top again. Now let's find our B. For B, we could see that our B is pi over 30. Now what does this mean? For this, this means that we need to find the period. Okay, so for the period, we just substitute the B value into the equation, into the formula. So it will be like this: 2 pi over B, which is pi over 30, and the period will be 60. Okay, and then the next, our D, which is the vertical shift, will be our center of the ferry wheels. So since the D is 22, and we know that it is the center of the ferry wheels, we need to find the maximum and the minimum value. So for the maximum value, we just add with the amplitude, which is 22. At 20, it will be 42. This is our maximum value. And for the minimum value, that is 22 minus 20, and it will be 2. So for the minimum value, our minimum value will be 2. From this also, we could conclude that our range starts from 2 and 42. And our domain is supposed to be negative infinity until infinity. But since we investigating the time, how much time for the ferry wheels to complete in one cycle, so we have restricted domain. Our restricted domain starts from 0, which is 0 second, until 60 second, because our ferry wheels, in order for our ferry wheels to be complete, is complete at 60 second. Since we already extract the information that we need, now we can start plot the graph. So from the equation that we got and the information, we could see that our amplitude is in positive, our period is 60, and our maximum and minimum value is 2 and 42. So now let's look at our desmos. So from this, we could see that our graph looks like this. As I said before, it starts from the top of the ferry wheel, which is 0.42, and it goes until 30 to 2, and it will go up again until 60 at 60.42. Now, what is the relation between this cost graph and the ferry wheels model? Let's look at it. Okay, so from the graph, we could see that it is in positive manner. Okay, so what is the relationship between the ferry wheels? So as you can see, our height for the ferry wheels is 42. This is 42. And from the center of the ferry wheels, it is 22. 22. From here to here. And as you can see, there is a little bit gap from the bottom of the ferry wheels and the ground, which means that this is 2. So there is a gap, and that gap is by 2 by height, and at the top is 42, like I said. Okay, so from this we could see that, assuming that we are at the top of the ferry wheels, which is assuming that we are here at the top, which is we at 0 second and 42, at the height 42, we slowly go down toward the bottom of the ferry wheel, which is eventually we will reach at this point, which is at 30 seconds, which is half of the cycle at 2. And from the bottom again, we will go up at the top again, which is at 42, but at 60 seconds. So as you can see, it is relate with the cost sign, the cost graph from the 42 point. We go down to the bottom at 30 to 2, and eventually we will go up again at 60, 42. So that is all from me. Thank you.
Assalamualaikum and good day everyone. My name is Nur Shafika Nasuha and I will be presenting the interpretation, real life meaning and critical reflection of our Ferris wheel model. Now I will begin with the interpretation of the mathematical model. The mathematical model is ht equal 20 cos pi per 30 t plus 22. The motion is periodic because the Ferris wheel moves in a circular path. The cosine function is stable because the passenger starts at the highest point when t equal to 0. The amplitude is 20 meters, which represents the radius of the Ferris wheel. The vertical shift is 22 meters, which represents the height of the center above the ground. The maximum height is calculated as 22 plus 20, which is 42 meters, while the minimum height is 22 minus 20, which is 2 meters. The period is 60 seconds, which means one complete rotation of the Ferris wheel takes 60 seconds. Now, we look at the key positions. At time 0, the passenger is at 42 meters, which is the maximum height. At time 15, the passenger is at 22 meters, which is the midpoint and moving downwards. At time 30, the passenger reached 2 meters, which is the minimum height. At time 45, the passenger is again at 22 meters, now moving upwards. And lastly, at time 60 seconds, the passenger returns to 42 meters, completing one full cycle. Okay, so this clearly shows the periodic and repeating motion of the Ferris wheel. Next, I will explain the real-life meaning of this model. The model can predict the passenger's height at any time. This is useful for right timing, safety management, and boarding and disembarking coordination. It helps operators know when passengers reach the highest or lowest point, which makes the operation more efficient and safe. In addition, this model can be applied in engineering systems involving rotational motion, not only in Ferris wheels, but also in other mechanical systems. This shows that trigonometric concepts are not only theoretical, but also have practical real-life value. Overall, mathematics helps us understand and predict real-world motion more clearly. Lastly, I will discuss the critical reflection of this model. The model is based on ideal assumptions such as constant speed, perfect circular motion, and no external disturbances. However, in real life, the motion may be affected by factors such as wind resistance, mechanical adjustment, and temporary stops. Therefore, the model does not capture every real-life detail. However, it still gives a useful approximation of the motion and helps us understand the overall behavior. Okay, this shows that mathematical models simplify reality, but they are still very valuable for prediction and analysis. So, even though the model is not perfect, it is still a powerful tool for understanding in real-life motion.
Now, we are moving to the part B. We apply geometry progression in a real-life context. The scenario we choose is the monthly saving with the compound interest, where we analyze how the saving grow over time. In this scenario, a student deposited of 500 ringgit into a saving account. This account earns 2% interest per month and the interest is compounded monthly. We assume that there are no additional deposit or withdrawals, and the interest rate remains constant throughout the period. Based on this assumption, the saving follow a consistent growth pattern. So then, we have to determine the pattern. We observe that the saving increased by a fixed percentage each month. By calculating 1 plus 0.02, we get 1.02, which is the multiplier. This means each new value is obtained by multiplying the previous value by 1.02. Therefore, the pattern is a geometric progression. Unlike the arithmetic progression, which at a constant difference, this model involves a multiplication by a constant ratio. From this, we can get from the mathematical model. The first term is of 500 ringgit and the common ratio is 1.02. Using the geometric progression formula, we can find the value of saving at any month using the n-term formula. We can also calculate the total accumulated saving using the sum formula. You can see over here. And this formula allows us to predict future saving accurately. So if we're using the formula, we can calculate the saving for the first 6 months. As shown in the table, the saving increased from 500 ringgit in the first month to 552.04 in the 6th month. This shows a continuous growth over time. Then from this value, we can observe that the saving increase every month, but the increase is not constant in the amount. For example, from 1 month to the 1 month 2, the increase is 10 ringgit. But from the month 5 to the month 6, it becomes 10 ringgit point 82 cent. This shows the different increase over time, while the ratio remains constant is at 1.02. This is the key characteristic of the geometric progression. Then we come to the graphical representation. We use the model T sub n equals to 500 multiplied by 1.02 raised to the power of n minus 1. First, we let the horizontal axis represent the month n, and the y-axis, vertical axis represent the saving values in Malaysian ringgit (RM). Then we substitute each month value into the formula. For example, when n equals to 1, the value becomes 500 ringgit. So we plot at the 1 at the x-axis and 500 at the y-axis. Then when n becomes to 2, the value becomes 510. We plot the 2 at the x-axis and 510 at the y-axis. Then we will continue the same pattern until the month 6, where the value is 552.04, giving the point of the 6 and 552.04. After obtaining all the coordinate points, we plot them on the graph and connect them with the smooth upward curve. From the graph, we can see the saving increase over time. Although the graph appears like here, almost like a straight line, but it's actually the slightly curved lah. You can see over here. And this is because the growth rate is only 2%. So the exponential effect is not very obvious over a short time of period. Therefore, the graph is not a straight line pattern, but represents the geometric progression too, where the growth is based on a constant ratio of 1.02 rather than constant difference. This confirms that the saving follow a geometric progression. Then from the graph previously, we can interpret that the growth increased over time. Each saving value depends on the previous value because the account earns compound interest every month. This means the increment becomes larger as time passes. For example, the increase from 1 month to the month 2 is RM10, but the later increase becomes slightly bigger. Therefore, this model reflects compound interest growth, where the money grows at the increasing rate over time. So, to conclude the part A, the motion of the very wells can be effectively modeled by a cosine function, since the movement is periodic and follow a circular pattern. The model accurately represents the height of the passenger over the time, and from this, we are able to identify the key characteristics, such as the amplitude, period, and the vertical shift. These values are directly related to the real-life measurement like the radius of the wheels, the time of the one full rotation, and the height of the center. Overall, this show that the trigonometric functions are not just the theoretical but can be applied to analyze and predict the real-life periodic motion. It also highlights the importance of mathematics in real-world applications such as analysis, prediction, and the problem solving. And for the part B, the growth of the saving can be effectively modeled using a geometric progression. This is because the saving increased by a constant ratio each month due to the compound interest, rather than a fixed amount. For the model, we can identify the key characteristics such as the first term of 500 ringgit and the common ratio of 1.202 and the exponential growth pattern. This showed that the increase become larger over time, which reflect how compound interest work in the real financial situation. Overall, this model demonstrates that geometric progression is useful for representing financial growth, and it helps to predicting the future saving and make the better financial decision. That's all for our group. Thank you for listening.